All right, so that we now know elliptic curve digital signature algorithm, let's see how a transaction actually occurs and how the nodes verify this transaction on a Bitcoin. So first, look at the Bitcoin scripting language. Bitcoin scripting language is specifically designed for Bitcoin and simply called script. And this is very similar to a very old programming language called Forth. Okay. It is stack-based, which means that every instruction is executed exactly once in a linear manner. As you can see, there are no for loops. So this actually makes it not Turing complete. You cannot implement everything using this scripting language, okay? And this is deliberately done because if it allowed for loops, this means that somebody can create a transaction in which a for or while loop runs forever, right? You can create infinite loops. So in order to avoid it, Bitcoin scripting language avoids loops. Ethereum allows loops, so it is Turing complete. So you might say that why it doesn't go into an infinite loop. Actually, you can write a Ethereum transaction which causes an infinite loop, but don't forget that in the Ethereum, you initially pay gas and you actually run your script as much as your gas allows you to. So you can really create infinite loops, but the amount of gas you paid actually determines how long that for loop will be run. Because when the gas runs out, even if the node is still in the infinite loop, they will just break out. This is the main difference between Ethereum and Bitcoin. So there are no loops, which prevents infinite loops. The number of instructions in the script gives us an upper bound on how long it might take to run and how much memory it could use. So this actually determines also how much transaction fee the miner would ask from you. Okay? When a transaction is announced to the network, miners have to run these scripts, okay? Because they have to check it. So there are some Bitcoin opcodes that I'm going to use here as an example. Dup actually duplicates the top item on the stack. Hash 160 hashes twice, first using SHA-256. So input is first hash using SHA-256. Then the result will be fed into RIPEMD 160. So the output is 160 bits. There is an opcode equal verify, returns true if the inputs are equal, returns false, and marks the transaction as invalid if they are unequal. Checksig checks that the input signature is a valid signature using the input public key for the hash of the current transaction. So this actually opcode does what I explained in the previous slides. Checks if the signature is correct. Okay? So it just turns true or false. So this is the good thing. You just don't implement actually any signature verification because it's already in the software. You simply use this opcode to check if the transaction is valid or not. Check multisig checks that the K signatures on the transaction are valid signatures from K of the specified public keys. So actually, a lot of people doesn't know it, but Bitcoin supports multiple signatures. And Schnorr signatures are a new version of these multiple signatures. So we will talk about them next week. But you can actually, get together with some people and, sign a transaction together. So far, we only showed a single user signatures, right? Elliptic curve digital signature algorithm was to show you a single user signature. Okay. Bitcoin wallet addresses are op hash 160 results of public keys. So your public key, x1 coordinate, actually x coordinate, fed into SHA-256, then actually 160. But we will actually go into detail about it because there's some encoding and so on. When a data instruction appears in a script, that data is simply pushed onto the top of the stack. Opcodes perform some function, often taking as input data that is on top of the stack. The most common pay-to-public key hash transaction is as follows. So this is actually the most basic transaction. The basic wallet software actually creates this kind of transaction. So in this transaction, you are actually signing a transaction where you're sending some Bitcoins to somebody else. So these are opcodes. These are data that you push. So let's see how this actually works when you verify. Okay. So first instruction is the signature. As I mentioned, that every data is put onto top of the stack. So this is, you can, here we have the instructions, we have the stack. So I add the sig here. So I'm actually following all of these steps. Then we have the public key, because we need to verify the signature with this public key. So when you fed into the stack, now the public key is at the top, right? So this is why we run the op duplicate, and in the memory, the top value is now duplicated, okay? Then I will calculate hash 160. So this is because now it is the address that you are sending money to, right? Because when you're making a transaction, you provide the value here, right, as a hash of the public key. Now we check if this equal to the public key that we obtained. The transaction value and the one you have it actually is the same. You check this with op equal verify. If it is the same, then you end up with pub key and the signature. Then you run check sig, and if this signature is valid for this public key, then you turn true. Okay. You might think why we perform this step. It is to check if you are trying to claim money that is not yours. Okay, here you are saying that actually this public key hash actually belongs to this public key. Okay, so it is yours. This is why we check this here. So this is as simple as that, and verification of the signature occurs at this point.